Hello everyone, long time no see, eh? So you probably read the title. In this video I'm going to show the steps that I took in doing my other project, apart from that headlight stuff that I do. And this project is a head-up display for my vehicle. Actually it was meant for my previous vehicle, but more on that later. So the whole thing started as a university project. I've studied aerospace engineering, mostly focused on avionics, so this stuff related to, human-machine interface and all of those gauges and so on was present there. In this project I wanted to learn as much as I could about the CAN bus, which is a data bus, and just wanted to have fun with integrating some electronic hardware into a working device, let's say. Since I don't have the first prototype here with me, I'm going to show you the photographs on screen. So in this first device, this first prototype for that university project, there was some Arduino Mini, some CAN transceivers, and it was hooked up to a 2x16 LCD screen. And the information from that screen was projected through a mirror onto a plexiglass covered with a semi-translucent film. So it was a self-contained device that you could just put on the dashboard, and that's how you could see all the information. Okay, so the first thing to determine in such a project is the interface to your vehicle. So the most obvious place to look for a connection to your vehicle would be the OBD port, which gives you an access to various data, networks and buses of your vehicle. It's going to look like this. It has 16 pins. There is a standard that describes where certain networks are located on this connector. So knowing that OBD thing, we have two ways to go. We can either use the standard request response system of the OBD protocol, which is a diagnostic protocol, or we can go the custom, I would say, reverse engineering way. First of all, if you go the OBD way, then you have to keep in mind that this is a request response system, so you're sending a diagnostic request asking for a value of a particular parameter. Let's say it's vehicle speed or engine speed. As soon as this request is received by some controller in the vehicle, then the car responds to you with a value of that parameter that you asked for. You can find more info on that on Wikipedia, which has an article called OBD2 PIDs, which stands for parameter IDs. And then here, based on those bytes, then you'll be able to determine the value of some parameter that you asked for. So for example, let's say it's fuel pressure. It says that to obtain the value in kilopascals, then you have to multiply the A byte by 3. I don't know, engine speed. It says that it's 256 times byte A plus byte B over 4. The biggest advantage of this method is that you can pretty much apply this method to any vehicle, so it's versatile, but it has its drawbacks. So the data using this method is pretty much limited because it's just the diagnostic data and not some, if you're, for example, more performance-oriented user of your car, and then maybe you're interested in, I don't know, the oil pressure or oil temperature, then you're most likely unable to find it on that parameter ID list. So basically more sophisticated parameters aren't going to be there using this OBD protocol. And then the last point I noted here is slow, because of it being a request response system, it takes time for you to send a message on the bus, and then you have to wait for a response, and this makes the implementation of this algorithm to a microcontroller more complex. Okay, and there's this second approach, the vehicle-specific approach, where you want to solely read the messages from the bus, the messages that contain the information that you want to display in any other way, just like it's done by the instrument cluster and so on. So to do this, you actually need to be aware of the network architecture that is present in your vehicle, and what data buses are there implemented, and based on that you need specific hardware, to act like an ECU that is already present in the car. In my case, I started the project for a Fiat Stilo, which had a body computer manufactured by Marelli, and it's a body computer from, like, I don't know, 18 years ago or even more. And the gauges in that car are connected to body computer with low speed CAN, or as they sometimes refer to it, a fault tolerant CAN. And it's a bus that integrates the communication between all of the interior components of that particular car. All the powertrain data, which I'm especially interested in because it's vehicle speed, engine speed, fuel level and so on, all of that powertrain data is received by the body computer over some different network, and then the body computer broadcasts this data to all of the nodes that are connected to that fault tolerant CAN. So this means that that the gauges in the car, those factory gauges, are just reading the car's speed, engine speed and so on, and they don't need to request anything, which makes this process fast, and that is also a good advantage of this one for such a project, that it's going to be fast and it won't require much time to process that information and to display it on the screens that we're developing here. Okay, now that we know where our desired information is available, now it's time to analyze how to obtain that information, in what format it is broadcast on that bus, and how to read it. On a level that is relevant to this project, I know that there is much more to a CAN message than just this, but a typical CAN message consists of those three main parts. The first part is the ID, which is written in hex. Then there is how many data bytes are there, so it's 8 in this case. And then you have the data bytes, which are also in hexadecimal. So the ID tells you what type of data or what parameter, like vehicle speed, a particular frame transfers. Then you have this length that I talked about, and then you have the actual value somewhere here in this data byte field. And this is the tricky part of this approach, because the info on what an ID represents, and what physical parameter it is, and what bytes carry the actual value of that parameter, and how to really convert it to an interpretable number with a certain unit. This information is at vehicle manufacturer's discretion, and it is not shared publicly. For example, this frame is actually a valid frame for my project, because 281 is an RPM frame which has a length of 8, and then in this byte called G, the value is 7C in hex, which converts to decimal, I don't know, it's 125 I believe. Yeah, 124. So it's 124, and then I know that I have to multiply this 124 by 32 and then I have the result in revs per minute. So 124 times 32 RPM gives me 3,968 revs per minute. Yeah, I hesitated here because the numbers that I took, it was meant to be 7D, and then I would have 125, and then it would give me, you know, a nice round 4,000 RPM. But whatever. This is how you convert this. But the question is how to obtain this this factor, and how do I know that this byte actually carries the information that I need? To answer this question, car enthusiast forums are here to help. Somebody might already have reverse engineered the network of your car, or might have gotten a hold of so-called DBC file, which is a database of all of those messages. If these are not available, then you can try to reverse engineer the CAN bus of your car on your own. So yeah, this can be a timely process, but a complete lack of knowledge on that bus, on that CAN protocol, that might be a pretty much a showstopper for a project. Fortunately for me though, there's a forum called canhack.de, where I managed to find all the info I needed on the interior CAN of the car that I was doing the project on. So here you have the thread that's called Innenraum CAN im Fiat Stilo, and then somebody was kind enough to tell me all of that info and what I need. So here is the list of for example, how to read the speed, which is 2A0, 4 byte long frame, or engine speed, which is what I just showed you, 281. Now that we know the most important aspects of the interface to the vehicle and the approach that we're taking to you know, obtaining the information that we need for the heads-up display, the next step would be to determine what hardware is needed for such a project. In my case, the network that I'm going to be using is low-speed CAN bus, and to connect a new device to that bus, an LS CAN transceiver is needed. For my project, I chose NXP TJA 1054. Okay, so the transceiver implements the CAN bus on an electrical level. The CAN bus is a differential network, but the data that is, you know, received and sent by your microcontroller has to be in some serialized form. And what transceiver does is just it converts that data from a serialized form or to serialized form, from that differential way of representing it on the bus. So here is a diagram according to ISO 11898. Here's the transceiver, and it's the last element in this whole, you know, architectural diagram. It's the last element that connects your microcontroller to your two wires of the bus. Yeah, then to exchange the data with the microcontroller, what you need is some sort of CAN controller in the middle. For example, MCP 2515 that I used in this first version of the project, that converts this serialized CAN data to a more microcontroller friendly form like SPI interface. However, there are many processors that have this CAN bus support and have this data link layer integrated just like it's presented here on this diagram. And this is the reason why I chose STM32F103. As you saw in the beginning, it wasn't like a single chip. It was in a form of a development board called the Nucleo, and the Nucleo being, you know, embed OS enabled, makes it easy to code and flash, without sophisticated programming skills. The project being a head-up display obviously needs some sort of, yeah, you guessed it, displays. My first prototype brought a 2x16 LCD panel. It did the job, however, yeah, I said 2x16 LCD panel, so it was something like this. It had some significant drawbacks, as I said. First of all, you couldn't flip the image anyhow by software, or there wasn't any register to set up to flip the image. So without that flip, the only way to project the image from here onto a windscreen was to use a mirror in front of it, like this, which reflected the image from the screen and flipped at the same time, and then the windscreen flipped it back to normal when looking at it. Then, even though the display that I used was a negative display, so there were bright letters on a dark background, this LCD screen has a backlight. Even though that it was negative, you could still see the reflection of that backlight in the windscreen of the car. This made it cumbersome, especially during the night, where you don't see just the numbers but also a blue rectangle, because the backlight there was blue. And then, because it was an alphanumeric display, its configurability was pretty limited to arrange the data in an interesting manner. Yeah, so for those reasons that I mentioned, I switched to two OLEDs that communicate over SPI. I switched to two instead of one because of the tiny size of one OLED. One of them is going to display the vehicle speed in a big number, and the other one is going to show the engine speed and the fuel level. With these OLEDs, I can flip the image in software, which means I can, after assembly, I can lay them flat over the PCB, and then I won't need any intricate optical design to project the information straight onto the windscreen. Also, because these are OLEDs, they don't have any backlight. The only light emitting from these will be the numbers, so it will be better to use it even during the night. Then why SPI and not I2C? For the reason is simple. I didn't want to play with address changing and so on, and based on the fact that this controller has multiple SPIs, I just could wire those two screens on two separate SPIs and use the resources that this processor has. So yeah, with hardware, what is left to do is to connect everything according to the data sheets, and then you have to code your program. Then the last step, as I said, is to code your program that reads the data from the car and then outputs it onto those screens. With the coding, all you need to do is to read the frames using some library and then do the calculations on those frames that I showed you and send that info to the screens. There are libraries for that. Actually, for these two, I had to modify some library that was present on this Embed OS website to code those boards. But yeah, it was nothing major to modify, so it worked pretty well. Okay, so to sum everything up, we started with a head-up display project. First of all, we had to determine the vehicle interface. You have two major directions to take. The first one is the more versatile, generic OBD way, And then you have this vehicle specific, in my case it's CAN bus, and then after you determined all of that CAN protocol, you know, the network architecture and so on, and you know all the interfaces that you're going to require, then you have to create your hardware platform, where you use a transceiver to interface with the vehicle directly. No matter if it's a LIN, CAN, Ethernet, anything, you need a transceiver to do that. And then obviously you need a microcontroller to connect this transceiver to, and a place where you can put the code that calculates all the data, and then display it. In my case it's OLEDs. It can be LCDs, but I don't recommend them due to their backlight, and just the image won't be as clear, especially in the night. Okay, now let's move on to my test setup that you saw in the beginning of the video. So what you can see here is my test setup. Let me quickly connect it to a power supply, these two microcontrollers, and then I think you'll be able to see some action. Okay, so there are two microcontrollers. This Nucleo right here is sending some speed and engine speed frames onto the CAN bus that is present between the two, with those two cables, black and white. And this other Nucleo, that is the whole brains behind this project, is actually reading that data and displaying it here. This instrument cluster, which comes from an Alfa 159, is just to verify the results. So here I'm sending 240 kilometers an hour and 8,000 RPM, and that's what does this needle sweep, and that's why I know that I'm sending the correct frames by this test Nucleo, and then I know that I'm going to be reading the correct frames in the car. And yeah, this is an Alfa gauge cluster, not a Fiat cluster, but fortunately enough, both of those cars from like 15 years ago, they utilize the same network architecture, the same CAN buses and so on, and that's why it works, and the protocol, as we can see, is the same because it works. Yeah. What's left to do in this project? First I have to do some wake-up concept, because the transceivers here are capable of, you know, being connected just to the permanent 12 volts, and then if there's any traffic on the CAN bus, they can detect it and set a pin, some enable pin for the you know, power supply section of the device. So that's how it can wake up the device without having the, you know, intermittent or ignition 12 volts signal. Yeah, so that's the wake up concept. Then I obviously have to do the electrical schematic and then the PCB layout, because now it's a, you know, a dev board setup, all with those cables and so on. I'm going to copy the layout of this Nucleo that is available online and just, you know, design a new layout to include the transceiver, passive components and stuff, and the programming header. And that's how I'm going to finish this. And then of course I'll need to order the PCBs, most probably from some JLC PCB or somewhere. And then of course, to make it, you know, look at least somehow professionally, I'll need to enclose it in some kind of case that I'm going to design in 3D and then print it. I don't know what material it will be. Most probably it will be PET or some nylon. I'm not sure yet. I haven't decided. So that would be it. Thanks for watching.